Okay, so yesterday we solved this question, one question of heat exchanger. Let's move forward. Right, in this question we simply calculated overall heat transfer coefficient U. And we also learned about this thing that if it is concentric tube through which fluid is flowing, then the formula is or the Nusselt number correlations are different. Okay, that will come again in another question, so we'll see again. So now let's continue our discussion, analysis of heat exchangers, which we started yesterday. So in any heat exchanger design, there are two types of design problems which we have to solve. What are those two? For example, temperatures which we want to achieve are specified. Okay, so we want that this fluid should enter and leave at this temperature. Okay, this is specified for both fluids, or at least one of the fluid. We want it to be heated up to this point or cooled to be this point. So this is known, and also mass flow rates we have decided, specified already. So what is required to find out the size of that heat exchanger? Whatever type we have chosen, type of heat exchanger, then we need to find out its size, right? To select a heat exchanger means both type and size. Second type of problem which we have to solve in heat exchangers, in which heat exchanger type and size is already known or given, and we want to find out, and flow rates we decide, and inlet temperatures are also known. So what is unknown? Outlet temperature and heat gain. This is the second type of problem, because heat exchanger already is there in some store. We have some old heat exchanger available and we want to use it for some purpose. So what is the requirement in this type of problem? We want to know its outlet temperature and heat transfer rate. Q is unknown, right? So for these two types of problems, the first one here, we want to find out the area of heat exchanger. Area is unknown, and type of heat exchanger we want to decide. In the second case, both heat exchanger type and size are given. What we want to find out, TO and Q, that is unknown. So there are two types of methods to solve these problems. For the first type, in which area is unknown, the method which is used is called LMTD method, or log mean temperature difference. It is very similar concept which we already discussed for in internal force convection. So this is actually one method. It is the name of one method to solve heat exchanger problems. What type of problems? This one. So for this method is best. For the second type, there is another method in which this T naught and Q dot are unknown, and that is called effectiveness NTU method. So we'll quickly go through these two methods generally. So this second method is best suited for this task 2. Okay, so for task 1, LMTD method; for task 2, effectiveness NTU method. Okay. Now, let's continue our discussion. In the analysis of heat exchangers, we are making certain assumptions. What are those assumptions? Major assumptions. One, of course, steady flow. And of course, we are neglecting kinetic and potential energy changes. Specific heat of the fluid is taken constant. We are not assuming variable specific heat as a function of temperature. Axial heat conduction, because there is a heat transfer from hot fluid to the cold fluid in radial direction, but there will be some heat transfer in axial direction. So we are neglecting this axial heat conduction within the tube wall. That is negligible. Maximum heat transfer is in the radial direction. And outer surface of the heat exchanger, this outer surface is perfectly insulated. So our heat exchanger analysis, which we are doing in this course, It is based on these assumptions. Okay, so if we apply first law of thermodynamics, if you remember, we can write these equations. Heat transfer to the cold fluid is simply given by this cold fluid, which is entering here, leaving here. This heat transfer to the cold fluid can be written in this form, right? M dot of cold fluid, Cp of cold fluid, and temperature change of the cold fluid. This M dot Cp product is written as capital C of the cold fluid. Okay. Similarly, we can write for hot fluid, right? Heat lost by the hot fluid is given by mCp delta T of the hot fluid, where this capital C is actually m dot H of the hot fluid and Cp H of the hot fluid. That's what we know from thermodynamics. And this m dot Cp product is also called heat capacity rate, right? M dot Cp, right? If it's only mCp, then there is a term which is called thermal capacitance. Okay. And we know what is this C, the amount of heat which is required to change the temperature by 1 degree Celsius. The fluid with the larger heat capacity rate, with the larger mCp product, either hot or cold, will experience smaller temperature change. The one which has higher mCp product, higher this one, so it will experience smaller delta T change. And we know why, we already learned about it. So smaller heat capacity rate will experience larger temperature change. If it's a very rare situation, but if the mCp product of hot fluid and mCp product of cold fluid are exactly equal, so here is the hot fluid moving, look here, hot fluid temperature is dropping, cold fluid temperature is increasing, but this delta T between two fluids will remain same throughout, because mCp product of both fluids is same, right? If both fluids are water, both are liquid, and their specific heat M and mass product is same, then this will be the situation. Otherwise, in normal cases, mCp product will be different. If on one side you have liquid, on the other side you have other type of liquid or a gas, so you will not have such situation. So this situation is only possible, this delta T between two fluids across the length of a heat exchanger will remain constant if mCp product is same. Okay, now let's move on. But there are two special cases where we cannot use mCp delta T. Whenever there is a phase change, because temperature does not change during phase change, like in condensers and boilers, so then we cannot use mCp product. And you would remember that is M into HFG. So here, for example, one fluid is boiling. Why it is boiling? Because it is absorbing heat from the other fluid, but the other fluid is changing temperature. So other fluid temperature is dropping, and the fluid which is boiling, its temperature remains constant. Same we can see here. If one fluid is condensing, so it means it is losing heat to another fluid whose phase is not changing, whose phase is same, so its temperature will be increasing like this. So now you can see delta T is not same. Delta T is different from inlet to exit. And in this case, for that fluid which is boiling or condensing, we have to use this equation, m dot into HFG, where HFG is called enthalpy of vaporization or enthalpy of condensation. Okay. And during phase change, a large amount of heat is actually transferred during phase change process. So we'll be using this phase change process in refrigeration and air conditioning, because it is dependent upon phase change process. Always, all the time, there is evaporation and condensation going on. Whenever a refrigerator is on, both of these processes are occurring on both of these heat exchangers. On one side evaporation, on the other side condensation, but only on the one side. Other side is air, is not changing phase. Okay, now the log mean temperature difference, we have to find out its equation. See here, what is that situation? This is a double pipe parallel flow heat exchanger. Both fluids are moving in one direction. So what you see here, the hot fluid temperature will be increasing and cold fluid temperature is increasing, hot fluid temperature is decreasing. And here you have maximum delta T and here you have minimum delta T at the end, but this change is not linear. All right, if it is not linear, then we need to find out this log mean temperature. Why it is log? Because when you will write its equation, there will be log term appearing. Okay, so we will end up with the same equation which we derived in internal force convection, LM and log mean temperature difference. But here the derivation is different because there you had only one fluid, and what was that condition? If you remember, it was this one, constant surface temperature, and the other fluid temperature was changing like this. But here you see the temperature of both fluids. If it is not phase change, then temperature of both fluids is changing. So here we will derive the same equation again, but now a different situation. Now we are counting the temperature change of both fluids, both sides. Temperature of both fluids is changing. Okay. Because we want this delta T to be used here. Now what delta T? That is a question, because here delta T is highest at the entrance and lowest at the exit. So which delta T should be used? So we will derive it. Again, the method is same, which we already know. We'll take a small differential element of the heat exchanger in which both fluids are flowing in one direction. So here is, in this differential element, the temperature change of the hot fluid is defined as dTH and temperature change of cold fluid is dTc. And our differential heat which is transferred from the hot fluid to the cold fluid is represented by del Q. And here this is the delta T, the temperature difference between average hot fluid temperature and averaged cold fluid temperature in this small element.
Why don't we say Cc and Ch? Why? Differential element of Ch.
So that we can integrate it. We want to integrate from inlet to outlet. So we are taking a small differential element. We'll write its equation and then we'll integrate from inlet to outlet.
It's for area, but for temperatures also.
Now temperature will be used as the limits. Temperature is changing from THI to THO. Cold fluid temperature is also changing from TCI to TCO, but that change is not linear. Let's see when we'll develop the heat transfer equation, whether it's a linear change or not. So if it's non-linear change, so this will appear in that equation. But how we start, we always take a differential element. We write the heat transfer or energy balance on that element. So that's why I have to say this is the temperature, differential temperature change of hot fluid, differential temperature change of cold fluid. And the differential heat transfer is del Q dot. Okay. So because I want to know what is that delta T in that equation. Okay, because this is the equation of heat exchanger. Okay, so now we are deriving LMTD, log mean temperature difference, for parallel flow double pipe heat exchanger. Here the example which we are taking is parallel flow double pipe heat exchanger.
Direction.
Both direction of both fluids in same.
Makes difference.
Yes, when you will have counterflow, it makes difference. We'll see in a moment.
They are not flow on one pipe.
Of course, not flowing in one pipe, but in one direction, I'm saying.
What it will make the difference if they are flowing in one direction or a counter?
Counter we'll see after that. Okay, so let's first finish this one, then we'll see counter. Okay. because this delta t is not linear, delta t is highest at the start and lowest at the start, so we want to find out what is that averaged delta t we should use. Okay, that is explained here. Okay, now let's apply energy balance to this small element area which we have chosen. So here heat lost by the hot fluid and gained by the
Oh,
cold fluid, right? So from here I can write the equation. Yeah, this negative only appearing here, whose temperature is dropping in the direction of flow. Here the temperature is increasing in the direction of flow of the cold fluid. From here we can write the dTh and dTc. Okay, del Q is same. Okay, now I can write it in terms of difference. What is this dTh minus dTc? Here is the differential change of hot fluid, differential change of cold fluid, their subtraction. So this minus this is clear. Now I can write this term as like this one or not? Sure. Yeah. Yeah, because some students are not sure. That's why x square plus x cube is also d of x square plus d of x cube. Okay. So, okay, now this equation, now this is clear. Here del q is taken out. So here is we have that equation. All right. Now this is the equation which we have obtained by applying energy balance on a differential section of that heat exchanger. This heat transfer can also be written, this equation is from first law of thermodynamics. It's not a from heat transfer. What is the heat transfer equation? For the same element between hot and cold fluid, we can also write the same heat as UA, whatever is the average TH here and average TC here. All right. Now we can equate these two delta Q's. All right. So here UA, this TH minus TC, it will go on the other side, right? Or simply put this equation here, replace it here.
yeah.
Right.
What's the detector?
What?
D.
Differential change.
Oh.
D, this one. Differential change of hot fluid temperature, differential change of cold fluid temperature. Hot fluid temperature is changing from here to here, cold fluid temperature is changing from here to here. D represents differential change. Okay, now you put it here, now you can separate. Now you can integrate. Here is the differential change of hot and cold fluid, and here is the differential change of surface area. Surface area is changing from from initial to final, you can say. And here hot fluid is changing from THI to THO, and cold fluid is changing from TCI to TCO. Right. So apply limits. That so here you will, this log will appear, and here it's simply U into total area and into this thing. Okay, now we can further simplify this equation. Now here is the equation which we have so far. Now here I will do some more changes because I want equation in this form. Q is equal to UA delta T, the heat transfer equation, but it is not that form because there is no Q here. So let's apply Q here. So I know Q for hot fluid, right? Only for the hot fluid. So here I can write this 1 over m dot HCPH from here in this form. Similarly for cold fluid, this is the heat gain of the cold fluid. So here I can, this 1 over m dot CPC can be replaced with this one, and 1 over m dot HCPH can be replaced with this. So just put these two here in these two equations. So we will have that Q which we want. Now write it in Q is equal to H UA delta T. So Q will go there. So whatever is left is on this side, U into A, and this whole term divided by this term. And if you remember this one, we can write it as delta T at inlet. What is delta T is at inlet? THN minus TCN minus TH out. If you take minus out, TH out minus TC out. That is the delta T. Similar equation which we derived before. So this whole term is actually called LMTD, log mean temperature difference. It's named as log mean temperature difference or delta TLM, or we also write it as LMTD, where LMTD is this one.
It's not average, it's total.
Sorry,
It's not average.
which one? No, it's not average. Which this delta TLM?
Q. This was called.
It's the total heat transfer. Total heat transfer from hot to cold fluid.
So why it's called mean?
It's mean, but log mean.
Yeah.
It's not arithmetic mean, because temperature. Yeah, this this delta TLM. Look, there is delta T1 minus delta T2 divided by log of delta T. It's a kind of average, but not arithmetic average. We named it because there is a log term appearing, so we named it log mean temperature. It is a mean, of course. It's kind of mean, but not arithmetic mean. The mean temperature difference between hot and cold fluid, but not arithmetic mean. It's log mean, logarithmic mean. Okay.
You will give the derivation question the file.
Yeah, this derivation is included. LMTD for parallel flow, and now we'll see counterflow. I'll not derive counterflow, but I have the derivation separately.
We have to divide it.
Yes, if it comes in the exam. I already told you there are three derivations from previous chapter, and from this chapter, this derivation. Okay, delta T1 and delta T2 is clear. Okay. For counterflow heat exchanger, we will end up with the same equation, but now here the counterflow. This was parallel flow. Now, what will be the difference if it is counterflow? Look here, this TC out will never be higher than TH out, right? Even if you have an infinite length. Maximum what you can achieve, TC out will be equal to TH out. But TC out can never be greater than TH out for parallel flow. Now let's see for counterflow. If this fluid, one of the fluid is moving in this direction. Now, let me explain it here first, then we'll see in these slides. If it is counterflow, one fluid is moving here.
Other side will mean the.
Yes, so now temperature versus length of heat exchanger or area of heat exchanger. So one fluid is entering through, for example, this is the hot fluid which is entering here, and this is the cold fluid. This is the hot fluid. Now cold fluid is going in this direction. Okay, so I can say that hot fluid, for example, is entering from here, THI, but cold fluid is entering from the other side, TCI, at some low temperature. For parallel flow, both hot and cold fluid were entering from the same side. Now hot fluid is entering from here, cold fluid is entering from here. So what will happen to hot fluid temperature? It will drop to THO, and cold fluid temperature will increase up to TCO. Because now this is counterflow.
They will
This
never
was
be equal. They will never be equal.
who will never be equal.
The TH and the TC.
Look here, TCO may be greater than THO. That is the main thing. Here, TCO can never be greater than THO. TCO will always be lower than THO.
So the thing is about TCO.
Yes, TCO now in this case for a counterflow heat exchanger can be greater than THO if it is a counterflow. So in other words, for the same inlet temperatures, we can say that LMTD, log mean temperature difference for counterflow, will always be greater than LMTD of parallel flow. Okay, so just by changing the direction, look, our profile changes completely for counterflow. So that is here explained that LMTD for counterflow, the temperature profile is different, of course. Now this is the hot fluid entering on this side, cold fluid is entering here, cold fluid temperature is increased. So hot fluid temperature is dropped. If you have a very large length, you can definitely expect that TC out will be definitely greater than TH out. But TC out can never increase higher than THN, that is for sure. Or this THO will never be lower than TCN. But this is possible now, just by changing the direction of flow, which was not possible in parallel. This was always lower than THO. Okay, but equation, if you derive this equation, you will end up with the same equation, but now what is the difference? What is delta T1? Now this is delta T1. What is delta T2? This is delta T2. Delta T1 is now TH in minus TC out. Before it was TH in minus TC in for parallel flow, because both were here, TH in and TC. So that is changed. Here delta T2 is THO out minus TC in. This is delta. So equation will be same. Derivation of this equation, I have it, I think. At the end, I have those derivations. So here is the derivation for LMTD. For counterflow heat exchanger, you will end up with the same equation, but there are a few differences which you can easily understand. It's not that difficult. So these two derivations, LMTD for parallel and LMTD for counterflow, that is a part of exam.
In the previous chapters, it's the
LMTD.
the differential will be equal to that part.
Yes, in the previous chapter we also had that LMTD, delta TLN. We didn't just say LMTD, but delta TLN from previous chapter, and from chapter 5 those non-dimensional analysis for free convection and forced convection. Okay, these are the derivations, 4 or 5 derivations I told you. So this one you can see from any book also, and also here I will. Okay, equation is same, only the definitions will be different of delta T1 and delta T2. Temperature difference at inlet, temperature difference at outlet. Okay, we have discussed these points. Okay, so for specified inlet and outlet temperatures, delta TLM of counterflow will always be greater than delta TLM of parallel flow. So in this equation, Q dot is equal to UA delta TLM. This will always be higher for counterflow. So it means we will get higher heat transfer, always higher heat transfer in counterflow. Parallel flow compared to parallel flow, counterflow will always give us highest possible temperature difference, which is required for heat transfer calculation. And not only double pipe, any other type of heat exchanger, this delta TLM, any other type, cross flow, shell and tube type, counterflow will always give you highest delta T. All other types of heat exchanger will have delta T lower than this counterflow. Any other heat exchanger, they will give us delta TLM lower than counterflow. So counterflow in this type, double pipe counterflow heat exchanger will always result in the highest delta T. But there are other issues. That's why we do not use counterflow, because here there are no fins, it's not cross flow. You need a very large length. That's why we go for the other types of heat exchangers, which we discussed yesterday. But as far as delta TLM, this term is concerned, for this will be highest for counterflow, double pipe counterflow heat exchanger. Okay, so in this, it means for a specific heat transfer, if this is highest for counterflow, you will end up with lowest surface area for counterflow heat exchanger, right? In counterflow heat exchanger, you would need the smaller surface area compared to other heat exchanger, parallel flow or also other types of heat exchangers. Okay, in counterflow heat exchanger, this delta T, this difference will be same throughout if MCP product of hot fluid and MCP product of cold fluid is same. Otherwise, this distance will not be same. This will be changing. Okay. Only when this is, but this is very rare situation. If you have MCP product same, otherwise you will have a different delta T. This difference between two fluids will be changing along the length of a heat exchanger. Okay, so that is clear. If delta T is constant, it means specific heat of both fluids are same. Okay, this counterflow heat exchanger derivation, it's a home assignment, but I have included here. Okay, so you can go through. There are many more derivations which I will later explain. These ones are so, but these are not part of exam. If I made those part of exam, then you will have a huge problem in heat transfer. Okay, so only selected derivations I have included. So now let's solve one problem. Another problem for counterflow heat exchanger. Counterflow concentric tube heat exchanger is used to cool the lubricating oil for a large industrial gas turbine. So in some industrial gas turbine, lubricating oil is being used. But this lubricating oil in a running engine, its temperature increases to a very large value. So we may need to cool it, cool the lubricating oil. So for that cooling, what we are using, cooling water. So you have a heat exchanger, we are using counterflow concentric tube heat exchanger to cool a lubricating oil by cooling water. So now cooling water is flowing through the inner tube. So I can show it here. So it's again concentric tube heat exchanger. This cooling water is flowing through the inner tube and its diameter is given bi, inner diameter 20 mm, and it is flowing. This is cooling fluid, so m dot c. M dot c is given as 0.18 kilograms per second, while the mass flow rate of oil is flowing through the outer annulus. Outer annulus whose diameter is given, outer diameter DO is 40 mm, and it is counterflow, so oil is flowing in the opposite direction. So this is hot fluid, m dot h, and it is given as 0.12 kilograms per second. Okay. The inlet and outlet temperatures of oil inlet temperature means THI is 95, and we want it to be cooled to at least 65 THO. So hot fluid inlet and hot fluid exit temperature is given. So it means THI and THO are given. Water enters at 30 degrees. So it is the cold fluid which is entering at TCI 30. Right. Now at what temperature it is going out, it is not given. Okay. Neglecting tube wall thermal resistance. This tube wall thermal resistance is negligible again. Okay. And outer we assumed
Yes.
insulated. So heat will be transferred only between these two fluids. Neglecting tube wall thermal resistance, fouling factors. Fouling factors is also negligible, right? Yesterday we studied fouling factors. We can include them. And heat loss to the surroundings. Calculate the length of the tube. So what length of that tube will accomplish this task? All right. In other words, we want to find out the heat transfer area. Equation we know. So now here you will show it the temperature profile. This is the hot fluid. This is cold fluid. So THI, THO, TCI, TCO. Equation we know, Q dot is equal to, because this is the LMTD method, delta T ln, or in some books you call it LMTD. So this LMTD method is used mainly to find out area. Now Q dot must be given, U has to be calculated. So now in this equation there are some unknowns, and this delta T ln TCO is unknown. So in this delta T ln TCO is unknown, this one. In area L we want to find out, in U we need to find out HI and HO. Wall resistance is negligible, so that is gone. Q dot, what is Q dot? That is also unknown. So many unknowns in this one equation. So we can find out Q dot, other equation, MCP delta T of hot fluid. So we can find out M dot H CP H hot fluid delta T of hot fluid. And do not get confused with negative sign, we just want absolute value of Q dot. That's why I'm writing delta T. So from here I can find out Q dot, which I use here. But I also need to find out TCO.
From other equation.
Which equation?
And CP for cold.
Yes, this Q is now known. The same Q is also equal to M dot C CPC TCO minus TCI. So from here I can find out TCO, because Q we have calculated from hot fluid. Same Q is transferred to cold fluid. So from here we can find out TCO. Now TCO, which we require here, this was Q dot, which we also calculated from here. Now U, HI and HO. Internal force convection. This is also internal force convection. All right. This fluid is moving through the circular pipe. This fluid is moving through a annulus. All right. Yesterday we discussed HO in detail. So find out HI, HO. So now everything is known here. Only unknown here is pi d L. Which pi d? Inner or outer? This area. What is this area?
The inner.
Inner, because heat is transferred through the inner pipe. So this is pi d I inner. I am using I for inner into L. So from here we can find out that. So that is the whole procedure. So now solution is there, plus minus putting values. Okay. So now let's quickly go through the solution. Oil properties are given. You will be given those. If otherwise, you should know we have to consult some standard table to find out these properties at certain appropriate temperature. What is that appropriate temperature for hot fluid? Average of this one, bulk mean temperature, which is this one. For cold fluid, one of the temperature was not given, so we have to assume something. So here is for water at 35 degrees. These are the fluid properties which we need later to find out convection coefficients. Okay, this is the table we will use only for annulus, fluid which is flowing in the annulus. Nusselt number for fully developed laminar flow in a circular annulus. The fluid which is flowing here. Okay, based on this DI, this is a separate Nusselt number, and Nusselt number on the inner surface, Nusselt number on the outer surface. For our case, it is inner, not outer. Okay, so yesterday we have discussed this thing. So now just, this is the schematic, this is the temperature profile. If this question, a similar question comes in exams, you have to draw this, you have to draw this
You have to
properly.
draw the plot.
Yeah, roughly. What is, if it is a counter flow, then this is the graph. If it is parallel flow, then
Yeah.
changes. All right. So here is the equation which we want to solve. Here is that L we want to find out. So U is this one, 1 over HI plus 1 over HO. So what is HI? Reynolds number. Mass flow rate is given. So from that mass flow rate, find out velocity. Right. M dot is equal to rho AV. V is equal to M. Oh, we already know everything. You have studied all of it in previous chapters. So find out Reynolds number. He is writing this velocity equation, this one, and putting it here to find out Reynolds number. Reynolds number, how much? It is greater than 10,000. It is turbulent. For turbulent, any of the equations you can use. This is one of the equation. For turbulent, put values. This is Nusselt number. You can see it's very high. So HI comes out to be 3,000 something watts per meter square per degree Celsius. Okay.
It's only a function of diameter.
It's a fixed number, Nusselt number. 3.66, and remember, Nusselt.
And what's this table?
This table is not for, is for this fluid which is flowing here. What we have calculated so far, HI. What is HI? Here. Fluid flowing through this pipe.
Yes.
Now HO, this one. Now fluid is flowing through a annulus, because yesterday you were not here and we discussed it in detail. The fluid which is flowing here. So now this is for annulus. For annulus, again different Nusselt number.
Only diameter.
Diameter ratio as a function of diameter ratio. So here again M dot, what is area? Yesterday we discussed. Now area of this one, pi by 4 d outs minus di square. So just put values. So this is actually hydraulic diameter we will use in Reynolds number. This is for calculation of velocity. This is the area. But here this dh is do minus di, hydraulic diameter. Yeah, see the previous chapter, previous video. So find out Reynolds number. Reynolds number comes out to be, because it's oil, viscous oil is flowing, so its Reynolds number is much lower. It's in, it's so low, it's definitely laminar. So for laminar flow, we have to use this part. So here di over do is 0.5, this one. And Nusselt number at the inner wall. Okay. Find out HO. HO is only 39. HI was in 3000. So our U will be near to,
One over
who were present here yesterday? Now our U will be near to this one or this one?
1 over H plus 1 over H. So the lower.
The lower one. This will be the main heat transfer resistance in the flow of heat. So our U is near to the lower one. Lower one is whenever HI and HO, if the difference is very big, then U will be decided by the lower one. Okay, so second we want to find out delta TLN. Delta TLN, this is the equation. Equation is clear. Delta T1, these equations will be given, of course, at the end. Okay, all clear so far. So just put variance, but here we need TC out. So which we can find out from here by equating these two. Okay, so this is TC out. But that is delta TLN, log mean temperature difference, to be used in this equation. And what is heat transfer? This is the heat transfer for the hot fluid is equal to UA delta T. So now the only unknown in this entire equation is this length of the pipe. U we have calculated. So this length, required length, now we have calculated as 70.65 meters. So the critical thing is the evaluation of convective heat transfer coefficient. You can see here convective heat transfer coefficient for one fluid is only 39, for the other fluid is 3000, right? So if we use wrong Nusselt numbers, or we can't simply use assumptions, because this will be affected. At the end, you are paying for this thing. Either you will get very small value or very large value if you start making assumptions here for convective heat transfer coefficients. Okay, let's solve another question. Here we have ethylene glycol. Ethylene glycol is another where is my mobile phone? Oh yes. Today's my phone. Thanks. Okay. Suddenly I was getting a shock. My mobile phone is gone. Okay. Ethylene glycol is heated from 25 degrees. Heated means it is cold fluid. All right. So this is TCI. Heated from 25 to 40 degrees Celsius. So this is TCO 40. At a rate of m dot is also given, so m dot of cold fluid is given. So you should use these terminologies, these symbols. This is the cold fluid in a horizontal copper tube. Horizontal copper tube of thermal conductivity is given, so it means wall resistance cannot be neglected in this case. So here is K is given 386 watts per meter per Kelvin, with the inner tube diameter 2 meter and an outer tube diameter. So it means thickness of that wall is also mentioned here. A saturated vapor, TG, gas, T of gas, saturated vapor at 110 degrees Celsius condenses on the outside tube. So here there you have a gas which is condensing here, like this one. So on the outer side, temperature of the fluid is fixed because there is condensation going on. So now we can expect the temperature profile. This will be TG 110 degrees Celsius, and here is the cold fluid, TCI to TCO. Okay. When the fluid is condensing, we have not discussed any Nusselt number or convective heat transfer coefficient if the fluid is changing phase. For that, there is a separate chapters which are not included in this course. In this book, you will see there is a separate chapter of boiling and condensation. There are different method, different equations to find out H. All right, and one of that equation is given here, that heat transfer coefficient in kilowatts per meter square per Kelvin given by this for that fluid which is condensing. It's not in the form of Nusselt number. Here you have some empirical correlation, where Tw is the average outside tube wall temperature. Here Tw is the tube wall temperature. Now you have some tube wall temperature will be somewhere between these two wall. This is Tw. So this heat transfer coefficient HO is given as a function of T wall and T gas. Right, where Tw is the average outside tube wall temperature. What tube length must be used? Again, we want to find out this tube length or heat transfer area so that this fluid is heated up from 25 to 40. Okay. The advanced version of this question could be, which is not a part of that course, that how much fluid will be condensed. That is another part we may have to find out. Okay. So here the properties of the ethylene glycol are given, which we'll use mu, Cp, K, or Prandtl number, and for water, of course, we have separate table available. So, in this question, what is the different thing?
T1.
T?
Wall.
T wall is not given.
We have resistance.
Yes, wall resistance has to be taken into account in the equation of U. There is wall resistance, which we cannot neglect. And another different thing is HO. HO will be calculated from this equation, and 9.2 and divided by Tg minus Tw to the power 0.25, but Tw, this is HO. But Tw is not given. So here we have to make certain assumption and then iterate for T wall. Hi is no issue. Hi is simply fluid flowing, a single phase fluid flowing through the pipe. Depending upon Reynolds number, we know how to find out Hi. For HO, here we have to make certain assumption, T of wall. Now T of wall, what you will assume?
So we can calculate it.
Sorry?
We can calculate it.
Yes.
From Q dot.
Yeah, that's I'm going to explain. First we will assume TW. What you will assume? Lower than 110 and higher than 40. Yes.
91.
Okay. So initially assume 90 or 95.
Closer to T.
Yes. Find out HO and then how to check it.
Q dot between
Between water and wall, and from wall to steam. So write this equation Hi per unit area, because area is unknown, Hi into T of fluid, inside fluid, T of water, let me write a T infinity, minus T of wall, no, heat transfer direction is this one, no? From gas to wall, then from wall to fluid. So it should be written like this, T of wall minus, because T of wall will be higher, fluid is lower, inside fluid, is equal to THO from glass to, sorry, not glass, gas to wall. So you will assume this T of wall, will calculate HO, put this HO here in this equation and solve for T of wall and check if iterate. If it is different, so if it, for example, it comes up to be 80, so use 80 here and solve it again until it converges. So T wall was assumed, then we calculated HO, then we use this HO in this energy balance. What is this energy balance? Heat lost from gas to wall is equal to heat gain from wall to inside fluid under steady state.
So can we say that it's equal to the overall? And
Yeah, but overall is unknown.
uh,
Look here, we know this equation now here, T wall is unknown.
oh yes, H also is
Is unknown. So from here, that is a new thing in this problem. The rest is same. That's how you will use, because we need this T wall to find out HO. So that's one iteration we have to do.
Except we have to find the Nusselt number,
No, not for outer fluid, only for inner fluid. For outer fluid, it is simply mentioned this equation because outer fluid is condensing. Here we have a specific or different equation. Okay, now, so that is how we will calculate HO, by assuming and by iterating. HI you will calculate separately. HI is not an issue. There you will use Nusselt number because fluid is flowing. A single phase fluid is flowing inside the pipe, no phase change. Whenever there is a phase change, different equation to calculate H, which we have not covered in this course. Boiling and condensation, it's a separate chapter. But we are using that equation from that chapter maybe. Okay. So now let's quickly go through the solution. Temperature profile is clear. One fluid is at constant temperature, other fluid temperature. This is the equation we want to solve. In this equation, this is delta T. Now delta TLM is clear. This is delta T1. Delta T1 minus delta T2. This is delta T1. What is delta T1? TG minus TC I, and this is TG minus TCO, but he is writing this one as TE, TG minus TE. Actually, it's not delta T1, delta T2 minus delta T1. Temperature difference at exit minus temperature difference at inlet divided by delta T of 2 minus delta T1. So this is delta T1, this is delta T2. He is not using CI, he is using I simply, and here E, and the other is TG.
And I thought that you didn't develop equation for constant temperature.
We developed in the previous chapter. It is the same equation,
For
constant surface temperature.
yeah.
It is a similar equation to that which we did in chapter 7, internal force convection. Okay, so the same equation, same definition, so that is delta TLM. Here, yes, all temperatures are known. TG, which is constant throughout, and TI and TE, which is changing 40 to 25. Okay, so that will give us delta TLM 77 degrees Celsius. Okay. Q dot we need in this equation, so we can easily find out from the cold fluid. M dot Cp of cold fluid is given. M dot Cp of cold fluid 40 minus this one. This is, and what is cold fluid? It's not water, it's ethylene glycol, and its Cp is given separate. All right. This is a UO equation. Overall heat transfer coefficient on the basis of O means we discussed yesterday, outer area of the inner pipe. We can write the same equation in terms of UI, then inner area of the outer pipe,
The inner part.
of the inner pipe. Heat is transferred only. Inner pipe has two areas. One is inner area, other is outer area. So we can write this in terms of UO, outer area, or in terms of UI, inner area. If you see the previous video, Okay. There is no time to explain it again. We have discussed in detail. Okay.
Sir, but yes, we can calculate H outer from Q dot because we know Q dot, we know delta T, MCP delta T. And then
Then
use it,
UA delta D.
no. Yes, use it for only between wall and water. Then we can find
Mhm.
T of wall without iteration.
Okay, I understand what you are trying to say. You are saying use this Q dot to calculate H of O, but area is unknown.
Let's take it per unit.
Per unit length. So here I have total Q dot divided by,
We don't know.
yes,
Yeah.
that is not known. I know what you are trying to say, but here still area is unknown. You have to divide. Okay. So this is HI procedure is clear. Renault, Prandtl, this is 10,000. So where is that equation? 75. HI is this one. For HO, this was the equation. In this equation, assume wall temperature of 100. Find out HO. This equation. This is an empirical correlation. Okay. 5,174. Now we have to check it. So how to check it? I told you this. HIAI from wall to fluid. Bulk mean fluid temperature. What is bulk mean fluid temperature of the inside? It is entering 25, leaving 40. So 40 plus 25 divided by 2, this one.
We'll take the average of the difference.
Yeah. Average. 25 plus 40 divided by 2. This is bulk mean fluid temperature. Is equal to HOAO. This heat which is transferred from the gas to the wall is equal to the heat transferred from the wall to the fluid, and that is this heat is this thing, and this heat is here from wall, and here what is the common thing? Wall. T of wall. Right?
And sir, but in the exam we still assume anything.
Why not? In this question you have to assume. If this question comes in the exam, so what you will do?
So
Give
now,
us T of wall.
No, I will not give to you. You have to assume, and you have to at least check once. So now you will check here area, leave this area. Okay, per unit area. Here you can write per unit. Okay, now he is writing pi di into L.
it's just the
So, sorry,
the areas, they will not be the same.
yeah, area is not same.
Like
Yes, you are right. Then length will be cancelled. Diameters are given. Good. Before I said area is 1. No, area is not 1. Wall thickness is not negligible. So there are 2 areas. Clear this thing? HAI, HOAO, pi DIL, pi DOL. L is cancelled. DI and DU are given. So yes. So now T wall we can find out. So T wall comes out to be 82. We assumed 100. So we should do another iteration, but in the exam you will not do any iteration. Okay, whatever is there, just solve it. But if you have time, okay, it's up to you. But this is not the requirement for exam. But here he will do another iteration because the difference is so big. So you repeat the same procedure with 82. No, he is using 80, near to 82. And now the temperature again used, now it comes out to be 77. Now difference is smaller. So you may go for another iteration. Okay. So in computer programs, everything is automatic. We do not need any iteration. Okay, this part is clear. This is the different thing so far. So whatever HO will come by assuming 80, this one, he is using this one because now he's saying that the difference between assumed and calculated is negligibly small. So we'll use this H. So now you can see this is HI and this is HO. Both are very close to each other. Now there is no clear difference between them. So now you can expect U. It's neither equal to any one of them. It's average between these two. It's 1600. Both are 3000 something. Now overall U is about 1600. In the previous question, one H was very large, the other H was very small, and your U was near to a smaller value. But in this case, one H is 3900, the other is 3490. So the overall U comes out to be 1600, kind of average between these two. So from this equation, now put everything, the unknown L, we can find out 9.3 meters. Okay. If you want this fluid to be heated from 25 to 40 degrees Celsius, then the length should be 9.3, or you can take 10 meter length. In this question, if you use fins here, only the difference will be here, HO. Area will be different. Now it will not be, you cannot write this equation in terms of diameters. You should write it in terms of areas. If you go the previous lecture, we have written this equation in terms of areas. So you should use those areas. So AO will be area of unfin and area of fin plus unfin, and that total area has to be used here in this equation. Okay. How much is that?
It's over 47.
Really? Okay, stop.